Hello everyone. So today I, Swati Verma, Assistant Professor at Calcutta's University, Department of Pharmacy, shall be discussing with you about the introduction to Chromophore and Oxochrome. As we all know that in case of UV, the absorption of your incoming radiation is done by these particular chromophoric groups, and the effect of chromophoric group is enhanced by your Oxochrome. So in detail we will talk about your chromophore and oxochrome. Moving forward, first we will see what are chromophore. So the absorption of light in the UV and visible region of the spectrum is due to the presence of the chromophore in the absorbing molecule. So the absorption of UV visible radiation is done by your chromophoric groups, which is present in your molecules. The term chromophore was originally used for unsaturated group of atoms which were thought to be essential for color. Now, the term includes such multiple bonds as those of ene, yne and carbonyl groups, in which the electrons are more loosely bound than those in fully saturated compound. So first it was a saying that chromophore groups are generally your unsaturated group of atoms, and we all know that as we increase the unsaturation, the group is lie in your visible region and it imparts certain color. These are also known as color carriers. This term was given to a system which is responsible for imparting color to a compound. For example, in azo dyes, the aryl conjugated exo group is your principal chromophore. In nitro compounds, the yellow color is carried out by NO2 group. So these are certain chromophores. Now, the term has been retained with an extended interpretation to imply any functional group that absorbs electromagnetic radiation whether or not a color is thereby produced. So further, this particular saying is modified by any group, any functional group which can absorb electromagnetic radiation is a chromophore. Chromophores are unsaturated organic functional group that absorb in the UV visible region. Chromophores are covalently bonded moieties with any compound and are responsible for the absorption of UV visible radiation. Examples are your aldehyde, ethylene and carbonyl groups. So we are having chromophores with your pi to pi star transition and chromophore with your n to pi star transition. When chromophores are added with any compounds, when you add chromophore to any compound, the absorbance wavelength of that particular compound will increase, and different chromophores have will show different effect over your different wavelengths. So here are certain examples of your chromophores which are present in your visible region. Like in the first, I have written the chromophores, then the example, then the solvent, and then the wavelength maximum with their molar absorptivity. Alkene in a 1-hexene in a solvent in heptane will give you wavelength maximum at 179 with the value of molar absorptivity 12,800. Like we can have aldehyde. So the example is acetaldehyde. The solvent, it is in vapor state. Lambda max is your 182 and the value for molar absorptivity or molar extension coefficient is 10,000. Likewise, we are having different chromophores which are present in your UV visible region. Moving forward, we can have oxochrome. So an oxochrome is a functional group or an absorbing molecule or ion that does not itself absorb radiation. Like in case of chromophore, chromophores are those particular molecules which will absorb your incoming radiation. These are responsible for absorbing your UV visible radiation, whereas chromophore as such do not itself absorb the radiation and the UV visible radiation, but these particular oxochrome can cause the absorptive maximum of the molecule to change their wavelength. Generally, oxochromes are functional groups like your NH, OH, SH and halogens that contain unshared electrons. The presence of an oxochrome in a molecule that contains a chromophore usually causes the absorptive maxima to shift to a longer wavelength, that is lower energy. Longer wavelength, lower energy. If the absorptivity of a chromophore increases with the addition of a substituent to the molecule, the increased absorbance is hyperchromic shift. So hyperchromic shift is as your chromophore is attached to a particular molecule. So whenever that particular chromophore, we are attaching a particular substituent acting as an oxochrome, so it will lead to increase in the intensity of your absorption band. So that is your hyperchromic shift. Generally, the presence of an oxochrome substituted on the diene causes a pethochromic shift, and as well as it will increase the wavelength, so that is your pethochromic shift. The effect of an oxochrome on the absorptive maximum of a diene can be estimated by using your Woodward-Fisher rule. Now we have a isobastic point. Isobastic point is also a specific point which we use for identification. Isobastic point is generally used for identification in case of indicators. So what is isobastic point? It is a wavelength at which your multiple absorbing species have identical absorptivities. So a wavelength in which if we are having a multiple absorbing species, and when we scan these particular absorbing species, so what we have at different wavelengths, we will have their different absorbances values, but at a particular wavelength, frequency or wave number, all these species will show a same absorbance value. So that point is isobastic point. An isobastic point is a specific wavelength, wave number or frequency at which the total absorbance of a sample does not change during a chemical reaction or physical change of the sample. So iso means equal and asbestos means extinguishable. Isobastic point is also known as your point of equal absorbance. So this is your example of isobastic point. In this you can see that whenever we are scanning this particular indicator, we are having three forms of indicator: acidic form, neutral form and basic form. So these particular are having different solvent, so in each solvent they will show their different absorption values. Like at 420 you can see that all these three forms are having different absorbance value. At 440 these are having different absorbance value, 460 at different absorbance value, but at somewhere around 515 these are having the same absorbance value. So the wavelength, wave number of frequency at which they are having the same absorbance value is known as your isobastic point, and it is generally used for determination of indicators. It is specific for indicators. So here are your certain references, the names of your books that you can refer for further study these particular topics in detail. At last, thank you so much.